In this video, I will discuss some NEET PYQs from the topic Mechanical Properties of Solids. These questions are based on Young's modulus of a material. Let us consider a body of general shape and there is a force applied to it. So because of this force, the size and shape of the body can change. Even if the body is rigid, say like steel or rock, it's not 100% rigid. There will be some slight deformation. Now let us consider a special case of a thin rod of length L and cross-section area A. So let us consider this type of a force, equal force on both the ends. So this sort of force will stretch this rod and increase the length by a small amount, say delta L. Suppose that the direction of the force is reversed, then the rod will get compressed. So this delta L will be negative. So here in this case, if the applied force is increased, then you can expect the delta L to be more. But stress, which is force per unit area, and the strain, which is the measure of the deformation, which is given as delta L by L, these two quantities are directly proportional. In the sense, if I double this one, then this thing will double. If I reduce this thing by half, then this thing will reduce by half. If the force is doubled and the area is doubled, then there won't be any change. So that's why this quantity is proportional to this quantity, and this is nothing but stress. Stress is force per unit area. And delta L by, which is the measure of deformation, it is strain. So stress is proportional to strain. So that means the ratio stress by strain is a constant. For a given material, and that constant is called Young's modulus of the material. So if the material is fixed, for example steel, this Y value is fixed. So if stress is double, means strain also will double. So with this understanding, you can solve these NEET PYQs. Timestamps are given in the description box. You can watch parts of video if you're running short of time. I'll discuss some 5 questions. This is the first one. 2 wires are made of same material and have the same volume. The first wire has got cross-section area A and the second wire has cross-section area 3A. If the length of the first wire is increased by delta L on applying a force F, how much force is needed to stretch the second wire by the same amount? You can pause and attempt this question. So 2 wires, same material means Young's modulus is the same. The first wire has got cross-section area A and the second wire, thicker wire, cross-section area thrice. Length of the first wire and the 2 wires have the same volume. So if the length of this first one, if it is say L, then the length of the second one, for the volume to be same, should be less and it should be L by 3. Because volume of a cylinder is cross-section A into the height or the length. So this volume of this one is A into L, volume of this one is 3A into L by 3, which is A into L. So for the volume to be same, this length should be L by 3. This first you have to figure out. So this one, upon applying a force F, so force F is applied, the length increases, it is getting stretched by an amount delta L. How much force is needed to stretch the second wire? So second wire applies force, say F2, for it to stretch by the same amount. So this delta L is same as this delta L. So what should be this force? Same material, so Young's modulus of this first one, stress by strain is delta L by L, and Young's modulus from the second wire, both should be equal. So here the stress is F2, area is 3A. Stress is force per unit area, so it's force by area. So here it is F2 by 3A. Here in the first one it is F by A. And the strain here is delta L. That is the condition given in the question. By the length, original length is L by 3. So A can be cancelled, delta L can be cancelled, L can be cancelled. So F will remain here, and here F2. And this 3 will go here and become 3, and this 3 if it goes, it will go in the denominator. So it will become F2 by 9. So F2 is 9F. A is the correct answer. This is what I explained here. The first wire of length L, cross-section area A, F is applied. So the increase in the length is delta L. Second wire, area is thrice, that's given in the question. And the volume is same. So for the volume to be same, this length has to reduce by 1/3 because area is increased thrice. So the product of area and length in both the cases is same because volume should be same. And they also given the extension in the second wire is also same as the first one. That's given in the question. For that to happen, what should be F2? Since the two wires of the same material, Young's modulus is same. So from the first wire, I'll get Young's modulus as stress by strain. Second wire, stress F2 by 3 by strain is delta L by L by 3. Since these two materials are same, these two should be equal. So equating these two and cancelling the common ones, A, delta L and L, we'll get this result. This is next question. A wire of length L, area of cross section A, is hanging from fixed support. The length changes to L1 when mass M is suspended from its free end. The expression for Young's modulus is, 4 options are given. So wire of length L, cross section A, fixed support. So this is a fixed support. So after applying this thing, the length will change. M is suspended from here. So length has increased, but this increased length from here to here, it's L1. Straightforward question. Next one is you have to know the definition. Stress by strain. Stress is force per unit area. Here the force which is stretching the wire is the weight of this block, which is due to gravity, and the cross section area is A. So this is stress divided by strain, which is change in the length by original length. Increase in length is L1 minus L by the original length is L. So you just have to rearrange So become mgl by A into increase in the length L1 minus L. C is the correct answer. Again, a simple and a straightforward question. Definition of Young's modulus should be known, and also you have to understand what is given in the question. Young's modulus is stress by strain. Here, the stress is because of the weight mg, which is attached to the end of the wire over cross section area, and strain is the measure of deformation, which is the increase in length of the original. So option C is the correct one. This is the next question. When elastic material Young's modulus Y is subject to stretching stress, S elastic energy stored per unit volume of the material is. There is a formula which you can use straight away. Energy per unit volume is half into stress into strain. To derive this formula, you have to use the basic idea that the energy stored in the system is work done on it. So here work is done on the system to stretch it. So if you use this thing, you'll get this result. You can straight away use this result for this question. Stress is they're already given as this. Strain is delta L by L. So we can use this one. Young's modulus is stress by strain. So from this you get strain as S by Y. So this is half S square by Y. C is the correct answer. Energy per unit volume is work done in stretching it. For example, if you take a spring and stretch it, some work is required to do the stretching, and that work done is getting stored as energy. Similarly, a rubber band or even a rigid rod, to stretch it, you have to do some work on it. So that work will get stored in the system as energy. So this can be derived from this step. So the result is half into stress into strain. So you can use this formula. Energy stored is half into stress into strain, and this is energy per unit volume. So stress and strain is using this definition of Young's modulus, stress by strain. Strain is stress by Y. So from this you get this result. This is the next question. The Young's model of steel wire is twice that of brass. Two wires of same length and same cross-section area, one of steel and another of brass, is suspended from same roof. If you want the lower ends of the wire to be at the same level, then the weights added to steel and brass wires must be in the ratio. You can pause and run this question. So Young's modulus of steel is twice Young's modulus of brass. So both the wires are of same length and same area. Length is same and cross-section area is same. And they hang from a roof. So this end is fixed. Okay, so because of the So here weight is added to it. W1, W2. The weights are different. If the weights are same, the extensions will be different because the two materials have different rigidity. But the weights are added such that the extension, the length, delta L, that is increasing the length by some amount delta L. It is same for both the wires. So what is the ratio of W1 by W2? So Young's modulus of steel is stress in this first wire, that is force per unit area. Force is the weight of the attached mass by area, that is the stress, and strain is delta L by L. And Young's modulus of brass is stress W2 by E, area is same, and the strain delta L by L. So putting these two things in this one, that will give W1, E will cancel, delta L by L will cancel. In this one, that will be 2 W2. So ratio W1 by W2 is 2. Steel is more rigid because Young's modulus is more, so more weight has to be attached to steel to push, stretch it with the same amount. So weight attached to steel is twice that of brass. Steel is more rigid. E is the correct answer. So it's given in the question. Young's modulus of steel is twice that of brass. So steel is more rigid. So Young's modulus is stress by strain. W1 by E by strain is delta L by L. L is same, E is same for both wires. It's given in the question, and delta L is also same. That's also given. So with these conditions, it is same. So this means that W1 is twice W2. Next question. Copper of fixed volume V is drawn into a wire of length L. When the wire is subjected to a constant force F, the extension produced in the wire is delta L. Which of the following graphs is a straight line? Delta L versus 1 by L, delta L versus L square, delta L versus 1 by L square, delta L versus L. So we have to cross delta L with some x-axis, which should be a straight line. So volume is fixed, and volume of a wire is actually a cylinder. It's area into length. Force is F. So Young's modulus of copper is stress by strain. Stress is F by A, and then strain is delta L by L. So fixed volumes, that means volume is fixed. L can change, E will change correspondingly. If L is double, means area will become reduced by half, so that the A into L is fixed quantity. And volume is fixed, and constant force. So force is also constant. Force is also fixed. So the variables here are Y is also fixed because it's copper. So the variables here are A, delta L, and L. So to plot delta L versus 1 by L. Okay, so delta L is Y. So I'll take delta L to the left side, and this L will go up, L by E into F. F is a constant, and A is not there. So A I can write as V by L. A if I write as V by L, L will go up, L square into F. F is constant, V is constant. So these two are constants. So variable is delta L and L square. And this is a straight line relation. So delta L versus L square will be a straight line. Equation of straight line is y equal to nx plus c, but here c is 0. So basically y should be proportional to x. Here y is delta L, and if x is L square, then the relationship is straight line. B is the correct answer. Volume is fixed. It's given in the question, which is area into L. Force is also constant. Young's modulus is stress by strain. So F by A by delta L by L, and A can be written as, since V is fixed, I can reduce the number of variables. So A can be written as V by L. It will become like this. So simplifying, I'll get F by V. This one is a constant. So this is also a constant because material is fixed. So delta L versus L square will be a straight line.